Hello everyone, we are Group 20. Our group member is Yang Junjie and Hong Weijie. Today we will be presenting our final project topic, Object Detection with Deep Reinforcement Learning. Okay. This is our outline. Firstly, we will discuss why we choose this topic. Then, we will mention two highly relevant papers we surveyed regarding this topic. Finally, we will explain the methods and goals we intend to achieve. Okay. Due to our current studies in computer vision and reinforcement learning this semester, we are curious about the applicability of IL in CV and how it can leverage its advantage. For instance, if we design a suitable reward function for IL, such as using intersection over union to determine the overlapping area between the current bounding box and the ground truth bounding box as a reward mechanism, this enables the training of an agent to continuously learn and improve. Moreover, this characteristic allows the agent to learn from a small amount of label data and become more robust to complex and various background noise environments. Next, let's briefly introduce IO and object detection. IO primarily involves training an agent to learn the optimal strategy in an environment, so trial and error and a reward function. The agent takes action according to a policy in different states, interact with the environment to obtain rewards, and utilize a Q function to aid in training the policy to maximize the cumulative reward. As for object detection, it is a computer vision task that involves identifying and locating objects within an image or video frame. It typically entails predicting bounding boxes around objects of interest along with their corresponding class labels. This capability makes object detection a fundamental task in computer vision, with application ranging from autonomous driving to image understanding and surveillance. Object detection can be categorized into following 6 methods, including traditional methods and deep learning-based methods. The first method is Viola-Jones. It's an example of the traditional approach, utilizing hard feature and AWS classifier to swiftly and accurately detect objects in images. SIFT extracts and describes local image features that are invariant to scale, rotation, and affine transformations. SURF is an inversion of SIFT, offering better efficiency and scalability to handle larger images. The last one of traditional method is HOG, focuses on capturing an object structure or shape by examining the orientation of gradient in local region of an image. Okay. Moving on to the following, moving on to deep learning methods. RCNN and FastRCNN were the first to introduce deep learning into object detection. They select candidate regions and use CNN for classification and regression to detect objects. This architecture is also utilized in the paper we are about to discuss. In contrast, one single-stage neural network, such as YORO, SSD, and RetinaNet, is a method aimed to simplify the pipeline by predicting object class labels and bounding box coordinates in a single pass, often achieving faster processing speeds than two-stage methods. Moreover, DETR is a DRT is a groundbreaking model that employs transformer for end-to-end object detection. It treats object detection as a direct set prediction problem, eliminating the need for many handcrafted components like anchor boxes. So this is a figure that describes how reinforcement learning utilizing object detection. A CNN model tracks features from regions, from bounding boxes, and we uh, introduce a reward function that enables the agent to take appropriate actions. And the design action involves up, down, right, left, better, taller, but it is not limited to following six mentioned in the figure. The upcoming paper will introduce different settings of the action, and through the action, the box becomes nearly to the target image that we want to capture. Okay. Next, I will introduce hierarchical object detection with deeper reinforcement learning, a paper that published at NeurIPS 2016. In the past, traditional methods used the sliding window approach, where images were analyzed at the local scale, looking at different parts independently without relating them. With the introduction of RCNN, the regional proposal approach allowed for easier utilization of relationships between regions. However, the state-of-the-art methods at the time required analyzing a large number of region proposals rapidly using the convolution feature map of the entire image. The authors of this paper propose combining a reinforcement learning agent with a hierarchical structure. This allows the model to analyze a significantly smaller number of regions, making the overall algorithm more efficient and reducing the computation cost. And the related work I want to introduce is the first I found combining RL with object detection. It's called Active Object Localization with Deep Reinforcement Learning. The method uses deep reinforcement learning to train an intelligent agent that can gradually adjust the bounding box until they match the target bounding boxes. Okay. The action the agent can take include moving up, down, left, right, flatten, and taller, like we mentioned in previous slides. But it have other two actions, including enlarging and shrinking the box. Okay. And then reward function use is also adopted, at least in the paper we introduced, which I will mention later. Next, let's discuss how this paper integrates RL. We define the state, action, and reward required for RL. The state consists of two parts: the descriptor of the current region, mostly extracted by the model, by CNN model, and the history vector containing the past four actions. Uh, According to the authors, this stabilizes the search trajectory, though as far as I know, it's not commonly used in RL design. For action, there are five choices. Distribute across four quarters regions of the box and one central overlapping region. The author provides two approaches, non-overlapping and overlapping, like the figure on the right. Non-overlapping, like we see in figure 1, is non-overlapping approaches. Figure 2 is overlapping approaches. Okay. So the figure, we know that if using the non-overlapping approach, dead zones might appear, potentially leading to the final bounding box falling into to include the target. While the overlapping approach requires more iterations to converge. It yields better performance. Like fixed one, non-overlapping figure doesn't capture the target because the target is too central. but in the overlapping one, there are two possibility to capture the target. Moving on to the reward part, the user intersection over union, a common evaluation metrics in object detection and image segmentation. To measure the overlap between the bounding region and the ground truth region. The numerator is the overlapping area, and the denominator is a union of areas. The higher the IOU value, the better the model's prediction is. When an action is taken, if the IOU value of the current step is higher than that of the previous step, a positive reward is given. At the terminal action, if the IOU value is above a threshold, we said in this paper, they say 0.5, a positive reward is received. Otherwise, a negative reward is given. Next, in the Q-learning part, the authors use deep Q-learning, which introduces neural networks. Okay. With deep networks, DQN can handle high-dimensional state spaces like images. Additionally, DQN incorporates techniques different from traditional Q-network, such as experience replay, which stores and reduces past reward experience to stabilize the training process, and having two Q networks to reduce instability during training. These techniques help the agent maintain stability in complex, high-dimensional environments. Finally, let's discuss the model architecture, which consists of the model extractor in the first half and the DQN in the second half. The author tested two different models for the first half. Both use VGG16 for feature extraction, but in different ways. The first one is image rooms model. We resize each region individually and then extract features through the convolutional neural network VGG16 in this paper, maintaining high spatial resolution features and yield better performance. The second model processes the entire image at once through VGG16 to extract feature maps, then applies ROI pooling to each region of interest. While this approach reduces computational load, ROI pooling lowers the resolution of the feature map. This reduction in resolution can blur features, particularly in small regions, which negatively impact detection performance. In the subsequent DQN section, as I mentioned earlier, the input consists of the state, which includes the visual descriptor and the history vector. The output comprises 6 neurons, each indicating the Q value of a specific action. The conclusion. This paper primarily explores a hierarchical object detection approach guided by deep reinforcement learning. By training an intelligent agent to determine regions of interest in images, effectively hierarchical image analysis can be achieved. Additionally, they compare two different candidate proposal strategies and feature extraction strategies. The results indicate that the overlapping candidate proposal strategy and the strategy of separately processing features for each region perform best in object detection tests. However, there are also some limitations such as the restriction imposed by predefined region sets on detection performance. Future work will address this issue by improving approximate detection and feature extraction methods. Okay, the following part will be presented by Hongwei Ji.
The second paper of our presentation is titled Multi-Stage Reinforcement Learning for Object Detection. This paper propose a sequential and hierarchical object detection method similar to the biological visual system and utilize deep reinforcement learning to train an agent. The agent iteratively performs zooming and moving action until it frames an object with a tightly fitting bounding box. Additionally, they employ multiple reward functions based on different metrics to better guide the training process of the agent, rather than relying on the intersection over union. These metrics evaluate and reward the quality of states. This related work involves performing hierarchical object detection in image guided by a deep reinforcement learning agent. The key idea is to focus on image regions that contain rich information and zoom in on them. However, this approach only allows for incremental zooming of image region. Hence, there is a desire to improve this method to increase detection rates. We use Q-learning to train the agent. This reinforcement learning technique estimates the values of state action pairs. The agent chooses the action with the highest estimate future value regarding the current state. We compare two general models. The one-stage model is based on a hierarchical object detection technique called image zooms proposed by related work. Additionally, they propose the two-stage model, which compensates for the one-stage model's limitation of reaching only a very limited number of bounding boxes. To improve the agent's ability to fit narrow objects, the state contains the image feature encoded by a BGG convolution neural network, and a history map vector that stores the last 4 actions taken by the agent. Using the one-stage model, the agent can choose between a terminal action and 5 zoom actions. The terminal action ends the search for an object and returns the current bounding box. Zooming action can shrink the bounding box, thereby zooming in on the image. By iteratively performing these zoom actions, the agent can follow zoom into the image until it finally decides that the bounding box fits the object well. The one-stage AR model extends the one-stage model by adding 2 zoom actions that allow change the aspect ratio of the bounding box. The bounding box can be compressed either in width and in height while holding the position of its center fixed. The two-stage model adds the second stage to the one-stage model. Let's perform 5 consecutive refinement steps after each zoom action. The reward function in this paper uses 3 metrics. The first one is intersection over union. Using IOU alone as a zoom reward often doesn't lead to favorable zoom action. Therefore, 2 additional metrics are considered: GTC and CD. GTC is the percentage of the ground truth that is covered by the current bounding box. The main difference between IOU and GTC is that the size of the bounding box has no direct impact on GTC. The GTC metric can be used to put a higher weight on still covering a large portion of the ground truth after a zoom step. CD describes the distance between the center of the bounding box and the center of the ground truth relative to the legend of the diagonal of the original image. The CD metric can reduce the probability of zooming away from the ground truth. This paper proposed a quality function that uses this introduced metric to better evaluate the quality of zooms. The first equation is used to estimate the quality of the current state and utilize bounding box B, ground truth region G, and image diagonal D as inputs, with alpha as the weighting vector. The second equation indicates that if the quality function value for the bounding box B pi after a zoom step is greater than the value of the bounding box B before, then the zoom action is rewarded, otherwise it is penalized. The third equation represents the termination action, where a reward is given if the IOU between region B and the ground truth region is greater than a certain threshold tau, otherwise a penalty is incurred. They use a sigmoid function on each metric in the quality function to see if this nonlinear attenuation helps to improve the learning place. In this sigmoid quality function, beta I influences the strength of attenuation through the sigmoid, and gamma I influences its centering. In this second stage, the sole objective of the refinement steps is to center the object with the bounding box. Therefore, only the CD metric is used in the reward function. Decreasing the CD is rewarded, while increasing it is punished. If the agent doesn't move, the reward depends on the possibility of achieving the smaller CD. In the architecture, both the zoom stage and the refinement stage follow the same structure. They take the image and the current bounding box as input, which are then fed into a VGG16 convolution neural network. The extracted image features concatenate with the history vector are input to the Q network. The output of the Q network contains a vector of Q value estimating each possible action. The agent selects the action with the highest Q value and transforms the bounding box accordingly, which serves as the output. The image with this bounding box is then used as the input for the next iteration. This paper presents a reinforcement learning approach for object detection by operating in two alternating action stages. The method is based on the hierarchical object detection technique, making it feasible to calculate feature based of the image before each step. By using GTC and CD training, the agent can increase the number of correct detections. Additionally, combining aspect ratio scaling, refining movements, and the enhanced reward metric can improve the detection rate. The objective of this final project is to reproduce and compare the advantage of hierarchical object detection as present in two papers, addressing their respective limitations and proposing adjustments to enhance their method. The reward function design in paper 1 is deemed too simplistic, limiting its effective in guiding the learning process. Sophisticated reward function or exploring hybrid approach, we aim to improve the effective and efficiency of object detection algorithm. Our presentation concludes here. Thank you for listening.